let's talk about temperature for a bit. Temperature is a pretty well-known topic. You've had exposure to temperature every day when you watch the news, so you kind of know what temperature is, and yet you don't know what it is. Mostly, I don't want to focus on the basis of temperature. We'll talk about that a little bit more when we talk about kinetic molecular theory, and we did talk a little bit about energy. But I do want to talk about the conversions and the different temperature scales. So we have 3 different scales that are predominantly used. There's even a couple more, but one is Fahrenheit, one is Celsius, and one is Kelvin. So I'm looking at these 3 different scales, and each scale sort of has to have 2 reference points to make it make sense. So 2 different known temperatures that it's based off of. In the Fahrenheit scale, the 0, which isn't really shown on here, but it would be, I'd take 32 down to 0. So the 0 reference point is reference to the freezing point of a solution of brine, the solution of sodium chloride and water and another, I think, ammonium chloride as well. So it's got a variety of salts mixed together. It can get colder than water can. So when you can get that solution to freeze, that's 0 degrees Fahrenheit. And 100 degrees Fahrenheit was based off of the temperature of the human body. Now, we know the normal temperature is 98.6, so it's not quite 100, but this scale was determined many years ago, and so at that point, based off of their accuracy of their measurements, 100 was considered the body temperature. Now, the Celsius scale said, let's reference these things to things that are a little bit more fixed. If you change what you make your brine out of, or you go from different human beings to different human beings, maybe it's a little bit different. But if we take pure water and we freeze it, it will always freeze at a certain temperature. It will always boil at a certain temperature. So Celsius uses the 0 of freezing water and boiling water and the 100 of boiling water to make it scale. Now, once you re-reference this, we need a conversion factor. So for every 100 degrees difference in Celsius, it's 180 degrees difference in Fahrenheit. So that's where we have to rescale things when we're doing our conversions. The final thing is that we have the Kelvin scale. The problem with the Celsius scale is this 0 isn't the coldest you can ever get. The 0 on the Fahrenheit scale is not the coldest you can ever get. You can get colder and colder and colder. Now we go back to what is the idea of temperature. The idea of temperature is related to the movement, the kinetic energy of the particles. So to get 0 temperature, I'd have to freeze I won't say freeze. Freeze means something else in chemistry. I'd have to still all the particles so that all the atoms are no longer moving. Now, that's a conceptual limit. We really can't get there. But if I could do that, that would be 0. So the Kelvin scale is based off of understanding what it would need to take to get all the atoms to stop moving, and that's where the 0 is based off. 0 is based off of absolute 0, means there is no temperature, there is no movement of the atoms. And we've successfully gotten down to 4 Kelvin pretty easily. I don't know that we'll ever reach 0, but we can get very close using some different techniques. So the Celsius scale and the Kelvin scale have the same ratio. In other words, for every 100 degrees Celsius difference, it's also 100 degrees difference in Kelvin. So 273 to 373. The only difference is that the Kelvin scale takes the Celsius scale and re-references it to a true 0. For this reason, Kelvin is the preferred unit of temperature for anything that's actually dealing with energy, because it's the one that's really referenced to true 0. So now we have some conversion equations. I've kind of written them out in a variety of ways so that you can understand how we're doing the conversion. So in the case of degrees Celsius, we first need to subtract off that 32 because the 0 water freezes at 32 in Fahrenheit, but at 0 in Celsius. So we have to subtract off the 32, so now they're both at the same 0. And then I'm multiplying it by the difference in the scales. For every 180 degrees of Fahrenheit, it's 100 degrees difference in Celsius. So that's where the original equation comes from. It's often written as degrees Fahrenheit minus 32 over 1.8 or times 5 over 9, right? If I divide these both by 20, this is a 5 over a 9. So 3 different equivalent equations for converting Fahrenheit to Celsius. I can also rearrange them and come up with 3 other different versions from going from Celsius to Fahrenheit. In the case of going from Celsius to Fahrenheit, I want to first rescale it, and then I want to add the 32 to get the difference in temperature between freezing points of water. So in this case, the scaling is 180 degrees Fahrenheit per 100 degrees Celsius, or 9 over 5, or multiplying by 1.8. They're equivalently doing the same thing. So pick one of these to know, or pick 2 if you want to have one for going from Celsius to Fahrenheit and one for going from Fahrenheit to Celsius. Kelvin is the one we're going to use most of the time, this Kelvin-Celsius conversion, and Kelvin is simply the degrees Celsius plus 273.15. If I'm giving you Kelvin and I want Celsius, subtract 273.15. Again, I think we've talked about this sometime along the way, but how many decimal places you use depends on whatever the degrees your measurement is given in. So if you're just told what is 68 degrees Celsius in Kelvin, 68 has no decimal point, so I could just use 273. If I said convert 68.5 degrees Celsius to Kelvin, that has 1 decimal place, so I would use 273.2, what this number would be rounded to the first decimal place. If I say convert 68.39 degrees Celsius to Kelvin, then I'm going to use 273.15. So round this off to match the same number as this, and you'll work out pretty effectively.